Now we're going to look at the robust servo mechanism using output feedback. So tracking using output feedback, we basically will require the plant to be at least stabilizable. We saw that we needed that even for the state feedback problem, and detectable. So we need detectability in order to ensure that we can get a stable observer. So the process using output feedback is the process of using an observer for feedback. We have seen that we can do that already, and we saw that when we use observer feedback in a state feedback type configuration, that we get the separation principle between the between the observer and the state feedback poles. And so we have that. In general, we would like the plant to be minimal, that is both controllable and observable. We will still require the plant to have no transmission zero at the given frequencies of the reference signal. And we want to use the state feedback design given previously and use whatever observer you wish. It could be a full order observer, reduced order observer. Then we want to compute the appropriate state feedback gain for a reduced order observer. Okay, so compute the appropriate state feedback gain for a reduced order observer. So this is the extra step that we need to do if we choose to use a reduced order observer. If we use a full order observer, then we can we don't have to do that step. So we now have these state equations. So this is our original system. This is our model, tracking model. Here is our observer, and in this case I'm using a full order observer. And our control signal now is Ks. Instead of Ks times X, it's Ks times X hat, Km times Xm, and our output. So in this particular case, we're not actually observing our disturbance. Okay, so when we put this system into the error coordinates, this is what we get. We have this extra term, that is, the error is actually affected by the disturbance. So this is an issue in this problem. So we do have that situation occurring. All right. So in matrix form, in error coordinates, this is what we have. And so we can see then that in these coordinates, the stability of our system is determined by the stability of this matrix and the stability of this matrix. Okay, so when we actually compute the eigenvalues of the overall system, we get the eigenvalues of this matrix and the eigenvalues of this matrix. So we have the characteristic polynomial of this part of the system, characteristic polynomial of this part of the system, but we can go through and show that this characteristic polynomial is in fact the state feedback poles for the robust servo. Those pop out independent of the observer. So once again, we have this separation principle, and we can choose the robust servo eigenvalues separate from the observer eigenvalues. So the actual controller then, which includes the observer and the tracking model, is going to be of this form. Okay, and so here's the output, the control signal. So notice that the controller takes in both R and Y, and so that's what we have. And so here's a block diagram that shows explicitly the observer. Okay, so here is our control signal. Notice that our observer uses the control signal and also the output. The model uses the output and the reference signal, okay, and subtracts the two. So this is our observer feedback control, and this type of control is called this is the controller, and I have these two broken out into separate blocks. I could also lump them together into a single block, in which case our system now has two inputs, okay, and so this is called a 2 degree of freedom controller. We have a 2 input, 1 output type of controller. So if we want to use instead a reduced order observer, then we would come up with our F, L, KZ, and KY and H matrices for our reduced order observer. And then this is the block diagram we would use. Or we can lump them together into a single system if we want. But this is, and so we can actually go through and show that using a reduced order observer, we also get the separation principle occurring. We have the state feedback eigenvalues associated with the robust servo, and then we have the observer eigenvalues, which in this case are just the eigenvalues of f. So that actually simplifies down significantly. All right. In terms of the controllable reference model, suppose that our reference for R of S, suppose we don't have a disturbance, but we just have a reference, then R of S, then this is going to be the controllable canonical form for this transfer function. Okay? If this is the reference signal we're working with, that is a sinusoid with frequency 3, that is square root of 9, this is our reference model. Okay? So AM and BM, again, this is controllable canonical form for this transfer function. So this is the robust servo mechanism. And I recommend looking at the practice problems to see an example of this.